Hello everyone, this is Jello. I am a PhD student at the University of Illinois at Urbana-Champaign, and I work with Professor Tucci Bashar, and today our work is entitled Full-Scale Experimental Investigation of an Advanced Geothermal Energy Storage System. Currently, it's all about energy. So the energy demand worldwide is exponentially increasing and is expected to grow by 50% between year 2018 and year 2050 as anticipated by the IEA and as we can see from the figure. This demand is exacerbated by the industrial development, by the economic growth, and by stronger heating and cooling needs. In the United States, currently, the petroleum and natural gas accounts for 70% of the primary energy source. And these sources have negative environmental impacts as they emit large amounts of greenhouse gases, and they are also highly affected by the fluctuation in the fossil fuel prices globally. So therefore, we need to find alternative solutions to provide for our energy needs. So one of these are renewable energy, and although energy generation from renewable sources, such as solar and wind generation, is growing, there are still some challenges. So the main challenge of these renewable energies is its intermittent nature. In other words, energy output by renewables depend largely on diurnal and seasonal patterns. For example, as we can see, for the solar energy production, it depends on the amount of sunlight falling on the panels at a given place and a given time. As for the wind-generated power, it depends on the wind speed and on the air density. However, for geothermal energy, there are no interruption of the source, meaning it is sustainable, flexible, and reliable, and it is independent of the diurnal and seasonal patterns, and covers a wide range of applications depending on the extracted temperature. However, this technology still lags compared to wind and solar energy, because current geothermal plants are site-specific, meaning they depend on the subsurface temperature and the geothermal gradient, and they depend on the availability of the groundwater. Also, the completion time is long due to the well drilling and exploration, and also there are high costs for the exploration and for the drilling. So, to address the challenges that are hindering the development of the geothermal energy, repurposing abandoned oil and gas wells into geothermal systems is one of the solutions. This will extend the economic life of the well. This will also eliminate the high plugging and restoration costs incurred on the oil operator. It will eliminate the potential environmental and health risks that abandoned oil and gas wells pose, because they provide pathways for methane and other gases to migrate either to potable water or into the environment. They will also eliminate the high drilling costs on the geothermal operator. So, advanced geothermal energy system presents an alternative approach to the conventional geothermal systems to provide a sustainable and renewable energy source. This system operates by first injecting the heat collected from renewable or industrial sources at the surface into the existing well to create a sustainable and artificial geothermal underground reservoir and increase the temperature of a low-temperature reservoir to the operational temperatures for either direct heating and cooling and optimally for electricity generation. Then this heat will be trapped or stored in a reservoir, and then it will be extracted later at a later stage depending on the needs. In Illinois, throughout the years, approximately 155,000 wells have been drilled, with the deepest well extending around 4 kilometers. Currently, there is 32,100 oil and gas production wells, 10,500 injection wells, 1,750 gas storage wells, 1,500 operators, and there are over 4,500 decommissioned oil and gas wells, and this number is expected to be higher. These wells hold great potential for demonstration and feasibility studies for an advanced geothermal energy storage that was proposed in the previous slide to determine the economic and operational viability of this system. Petrophysical, geological, and hydraulic data provided the required information about the subsurface characteristics, including the lithology, mineral composition, porosity, initial temperature profiles, temperatures, evolution in the subsurface, and hydraulic conductivity. The existing data was analyzed to evaluate the thermohydraulic properties of the geologic formations, and after a high-level screening for the target formation, the priority was given to the formations which were prevalent throughout the basin and penetrated by most oil wells and throughout the Illinois basin to be able to replicate this test throughout the state. So at the end, the Cypress Formation was an outstanding candidate for the field test, and the Cypress sandstone is prevalent across the southern Illinois basin and extends to Indiana and Kentucky, as we can see on the figure. So available data sets pertaining to existing wells, including oil and gas wells in the Illinois basin, were reviewed and analyzed to identify a technically viable oil well in Illinois. So after thorough investigation, the M. Ackleberry number 4 site was selected, and the well was drilled from August 19 to August 22 in 2013, and an evaluation of the site surface infrastructure for the suitability was performed, and the well was planned to be plugged and abandoned, but the company reduced these costs by providing the well for the field test. The site survey involved evaluating the road conditions for access to well site, power and water availability at well site, and site layout for operational activities. Then the site setup activity included improving the site road accessibility, spotting a frac tank, office trailer, etc., as shown in the figure. The field test was performed to characterize the thermal energy storage characteristics. It included a hot fluid injection test and a cold fluid injection test, each followed by a shutdown period to monitor the pressure fall-off and thermal stabilization. The figure shows a simple schematic of the field test. There was a heater and the water was injected, and we equipped the well with a DTS cable to record the temperature evolution. We also perforated at from between 900 meters to 903 meters. So as part of the field test preparation, the well was swabbed with a swab rig to allow for underbalance perforation. This helps minimize the perforation skin damage and improve formation cleanup. The well was swabbed to acquire native formation fluid for sampling, and a memory gauge was deployed to record the well pressures, as you can see in the figures. A distributed temperature sensing system was also installed, and the DTS spool was mounted on a winch truck and lowered through a sheave wheel hoisted by a crane, as you can see on the figure 2. The downhole assembly consisted of a DTS cable, housing assembly, and the pressure and temperature memory gauge. Regarding the field test operation schedule, the operation began on April 5 by injecting water at 50 degrees Celsius at a flow rate that started at 8 gallons per minute and was then decreased to 5 gallons per minute. The heat injection test lasted till April 8. Then no operation was performed from April 9 to April 14, where pressure fall-off and temperature decay were monitored. Then from April 15 to April 16, cold injection test was performed. The flow rate first started at 2 gallons per minute for 3 hours. This was followed, then increased to 4 gallons per minute for 3 hours, and then this was further increased to 6 gallons per minute for the remaining volume of water in the frac tank. Then from April 17 to April 21, no operation was performed, and again, the thermal and pressure decay were monitored. So the temperature heat map clearly shows the 4 stages of the field test. Initially, we have the heat injection test, and we can observe that during this phase, higher temperatures are recorded at shallower formations, and then at greater depth, cooling is observed, indicating that heat dissipated to the shallower formations. This can be explained with the relatively low injection rates used during the field test, as mentioned previously, and which resulted in uneven temperature distribution along the formations. After that, we can see the phase where thermal decay occurred during phase 2, and then the third phase where cold water injection test started, a lower temperature around 16 degrees Celsius is recorded, and it narrows down at greater depth. During stage 4, it represents the thermal decay after the cold injection test, and it occurs more rapidly as compared to the thermal decay after the hot water injection test. Also, the temperature time series at 300 meters, 500 meters, 700 meters, and 900 meters are plotted. Here too, we can observe that at depth greater than 500 meters, cooling is recorded during the heat injection test, as we can see from the plots. Then, the temperature profiles are also plotted during hot water injection. Results were consistent with what was observed earlier, as heating is recorded at shallow formation and cooling at greater depth. During the thermal decay phase, temperature approaches the initial temperature profile, as we can see. During the cold water injection, deeper depths are more affected by the injection of cold water, and then for the thermal decay, temperature again approaches initial temperature profile. As observed in the heat map, this phase occurs, the thermal decay after the cold water injection test occurred more rapidly than that after the hot water injection test. And we can see that also here. Now, as a conclusion, shallower formations should have been selected to reduce the heat losses. A site with easy access to municipal water and electricity can reduce the operational cost of the field test. A contingent site host to account for wet weather conditions should be planned ahead, and early customer discovery efforts are crucial to acquire the required data for developing a viable product. Thank you so much for your attention, and we will be happy to take any question.